Hi Emma. I'm going to use my new teaching toy, and you can tell me how this works for you. But rather than use Skype, I thought I would try and put this little video together as my explanation of non-cyclic. There's a good start, Paul. Yes, get the pen working. So this is an example of, come on, you darn thing, work. Yes, non-cyclic photophosphorylation, the light reaction. Two main things here. The take-home message is it's producing ATP, but it's also splitting water. Okay, so we've got photolysis, photolysis, splitting of water. So they're the two important things with non-cyclic photophosphorylation. It's all rather complicated, but I will try and make this easy to understand. This is going to be a challenge for me because I haven't taught this for yonks. Right, so we've got chlorophyll, two chlorophyll molecules here and here. What do those numbers mean? Well, it means that this chlorophyll molecule absorbs light energy, absorbs photons of light at 680 nanometers, whereas here we've got 700 nanometers. So that might come in when you look at your absorption spectrums to see how active these chlorophyll molecules are. Right, surrounding the chlorophyll molecule we have a photosystem, and I think in some textbooks you'll see it drawn as a funnel. In other words, light energy is coming in, we've got photons of light, and they're captured by this funnel, and the photons are funneled to this reaction center, or reactive center. So that's what this photosystem is doing. It's just funneling the photons to the chlorophyll molecule. Okay, so now these chlorophyll molecules have got all this energy. And what happens here is a pair of electrons, at least I think it's a pair of electrons get terribly excited, and they basically jump energy levels. In fact, they get so excited that they leave the chlorophyll molecule altogether. Okay, now that loss of electrons means oxidation, Leo. So what we have here is we'd say that the chlorophyll is being oxidized. So the chlorophyll is being oxidized, it's a loss of electrons, and then we've got this electron acceptor. You might also see it being described as an electron carrier. So this is now holding the pair of electrons. So this is lost electrons. It's now a little bit defunct as a result of that, but we'll come back to that later. And the electrons are basically passed along a whole series of electron carriers, and we have what's called the electron transport chain, and that chain is effectively going on in the thylakoid membrane. So here's a thylakoid. Okay, so there's your thylakoid there, and you remember thylakoids, have I mentioned this already? Here's the thylakoids like so, all stacked up to form a grana. So there's your thylakoid membrane. And as the electrons move from a high energy level to a low energy level, sort of releasing that energy as it goes, whatever that means, that energy does work. So that energy is pumping hydrogen ions into the thylakoid interior. So that's what's going on there. What's the significance of that? Why would we want this high concentration of hydrogen ions inside this thylakoid membrane? Well, we want that because we've got this fantastic little ATP generator here. So high concentration of hydrogen ions, they move down their concentration gradient through this lovely proton or protein channel, and those protons are able to transfer their energy so that ADP picks up another inorganic phosphate. So adenosine diphosphate has got enough energy now to bond another inorganic phosphate molecule to it, and now we have ATP, thus the generation of ATP. This is sometimes referred to as chemiosmosis. Okay, chemicals moving down their concentration gradient. So an ingenious little device, and this only happens as a result of this photosystem 2. It doesn't happen in photosystem 1. Now what? Well, those 2 electrons that are now sort of lost their energy, they go into photosystem 1. So in photosystem 1, we have exactly the same situation taking place. Photons coming in, channeled to this reactive center, a pair of electrons are lost. Okay, oxidation, and they're accepted. But thankfully, photosystem 1, for every pair it loses, it's gaining a pair from photosystem 2. Now, the energy here, the electrons here, move down the electron transport chain, as it was, sometimes seen as a pair of steps or a set of steps. They move down there. This time the energy is not used to make AT, but the energy is used to add hydrogen ions onto NADP. In other words, reducing NADP. So you've got NADPH2. You see that later in the Calvin cycle. And there you go. But we still haven't answered this question here. We've lost a couple of electrons. Yep, we've lost those 2 electrons. How are we going to keep this photosystem going? Because it's defunct without a couple of electrons. It needs to get them back. And it gets them back through photolysis, water splitting. So the light energy, those photons of light, can split water. And it splits water into the 2 hydrogen ions. Okay, you can see where they come in. Alright. We've got our oxygen, because photosynthesis produces oxygen, right? And we've got a pair of electrons, so they can zoom into photosystem 2. I don't know whether you need to know all of that, but hopefully it will make the cyclic photophosphorylation a little bit easier. Hopefully things will click. Anyway, I hope that's worked, Emma.